Welcome, VEST scholars, to this module where we're going to explore Earth as a system and Earth system science in general. Now, systems are something that you guys are very familiar with, even if you don't consciously think about it. You are a system, your body, your interactions within your body, your school is a system, your home is a system. When you go to your school, you have an effect on your school and it has an effect on you. When your teacher assigns you a homework assignment, like you're going to be assigned for this module, you take that back home and you work on it at home, and that has an effect on your life at home, which has an effect on your parents, which has an effect on that whole system in general. These are things you're used to understanding. And sometimes there's an outside occurrence that happens that's really major, that has that has the effect of moving things out of a sense of equilibrium. And these are all things that you think about. I'm going to ask you to take that subconscious knowledge, be a little more conscious of it, and apply it now to the Earth as a system. Take, for instance, the tree in the background here. This tree's been cut down. That tree contains within it, and it's an entire ecosystem of fungi, of molds, and of other organisms that live and rely on that tree, including perhaps arboreal mammals and so forth. This tree was removed. It's going to have an effect on the canopy. The hole is going to open up in the canopy of this forest, letting in more light. That's going to have an effect on seedlings and on water availability. It's going to have an effect on the ecosystem, because now you've removed all that biospheric mass and so forth. So if we think about deforestation in this situation, and we think about the Earth effects of that, it's not just this simple back and forth between these systems. It's actually a whole lot more complex than that. For instance, when you remove trees, you increase CO2. First, by removing the tree, going into the atmosphere, by removing the tree and the CO2 it would take out, but also by burning what's left to add CO2 to the atmosphere that was stored as part of the biomass. You also reduce O2 being produced as a result of that also. You affect the hydrosphere. You change the amount of water moving in and out of the hydrosphere through transpiration. You affect the geosphere, the lithosphere, through erosion, the movement of sediment as a result of that tree being taken down. And of course, habitat is reduced by removing that tree out of the biosphere. But it's not just direct stuff, it's indirect effects, runoff into the hydrosphere, sediment going in, the sedimentation rates going up into bodies of water, which have a downstream effect on, literally, aquatic organisms and so forth, both in the freshwater systems and eventually in the marine systems. Soil erosion has an effect on the biosphere. Warming has an effect on the atmosphere and on the biosphere. Evaporation rates go up. Respiration becomes a little bit is affected by it overall, the biosphere. That's because all these systems are connected. All these systems interact with one another. The Earth as a whole is the way that it is and supports the life that it does because these systems all exist and all interact. This is one version of looking at this, where you have the hydrosphere, the atmosphere, the biosphere, and the lithosphere. Here you have the cryosphere pulled out of the hydrosphere, the frozen Earth. Another way of looking at it is actually look at it this way. So again, you have the hydrosphere and the atmosphere and the biosphere. This time they call the lithosphere the geosphere, which is probably a better name for it. They pull the anthroposphere out of the biosphere because humans are basically a force of nature at this point in terms of our outsized effect compared to the rest of the biosphere. And then, of course, the cryosphere isn't listed here, but you could pull that as well. We should be remiss, though, if we neglected the exosphere outside of all of these, or depending on your perspective, containing all of these, making all of it possible, because it's the exosphere that drives much of what's going on here in these interactions, because Earth has an energy budget, and that energy has to come from someplace. Now, admittedly, there's a lot of energy that comes from the interior of the Earth, but that's a secondary source of energy. It drives plate tectonics, and it does, of course, have direct effects on all these spheres because of that. We'll get to that in a later module. But in this case, we're looking primarily at solar energy and its effects. Of course, solar energy comes in as a wide band of radiation, some of which doesn't make it through the atmosphere for various reasons. But what does make it through the atmosphere, a lot of the radiation that we feel eventually as heat was shortwave radiation as it entered the atmosphere, was absorbed by the surface, and then re-radiated by the surface as long-wave radiation, infrared. You feel it as heat, which then gets trapped by greenhouse gases and clouds to some extent. Clouds have an effect of reflecting energy back to the surface, but they also have the effect of reflecting energy back out to space, so they can be pretty complex to model. But regardless, these are really important things. This is a really important thing to keep in mind when you're thinking about how it drives all of these systems. It really comes down to energy. Now, let's consider for a moment this environment. And this is just one example. So if we look at the coral reef environment, you can probably look at this picture and pick out a few spheres. You might pick out the biosphere. Here we have coral polyps existing in a colony in any one of these situations. And you may or may not realize coral polyps don't just exist by themselves. They have a mutualistic relationship with an algae, a photosynthetic plant, essentially, that lives with them. And because it's photosynthetic, it produces oxygen and it produces biomass that the coral can then feed off of and produce nutrients that then the algae is able to use to produce its food, and so forth. It's this nice mutualistic relationship. They cannot live one without the other. You are probably right to assume that there's an atmosphere above that surface, because there is, and that atmosphere has a particular gaseous concentration, or concentrations of gases, in particular CO2, that's not too high. That doesn't, of course, adversely affect the ability for coral to produce its skeletal structure by causing the pH of the water to be too low. It's also important for there to be oxygen in that atmosphere, because other things that live in that atmosphere are having an effect on the coral downstream. And of course, the energy traveling through the atmosphere produces waves along the surface, which coral need because coral polyps are filter feeders, and the water has to be moving constantly. The hydrosphere itself, of course, the water itself, is what coral and all these organisms here, fish and so forth, are evolved to live in. They have adaptations that make living in the water possible. And you should note that tropical waters tend to be very nutrient poor. And the reason there's so much life in a coral environment is because the coral reef itself produces the food necessary for all these organisms to exist. And of course, the geosphere contributes by producing, through erosion, weathering and erosion, salts that are put into the ocean. The oceans are salty because of erosion off of the land. Some of those salts come in the form of the ions bicarbonate and calcium in aqueous solution, and those can combine together to produce calcium carbonate. And of course, all of this is driven by sunlight coming from the exosphere, the space environment. And that's why the space environment is so foundational. Let's take another focused example here, but let's talk now, instead of the systems perspective itself, what happens if there's an effect on a system, like say warming, that then causes something to happen that actually makes the effect even worse. We call this a positive feedback, or an amplifying feedback is a better term for it, because typically we don't think of these as positive occurrences, so we want to make sure we use good terminology here. Amplifying feedback is a better term for this. So if we look here, here's some sea ice in the Arctic. And as sunlight comes in, not a very sunny day here in this picture, but as sunlight comes in, almost all of it that hits the ice is reflected back into the atmosphere. That sunlight that hits the ocean, you see how dark the color of the ocean is, gets absorbed by that ocean. So it's really important to think about what the result of this is. If we warm the planet, further global warming, which has an outsized effect on the Arctic, because the Arctic warms more rapidly and more disproportionately than the equator does. So further global warming leads to higher temperatures, which leads to less ice and less sunlight reflected, which means more open water and more sunlight absorbed, which leads, guess what? Without even adding any more CO2 to the environment, further global warming. This is what we call an amplifying feedback. But obviously, if there's amplifying feedbacks, there must be another kind, and these are dampening or buffering feedbacks. And I'm going to use an example you're probably already, again, subconsciously familiar with, which is the predator-prey relationship. So, of course, the more predators you have, the fewer prey you're going to have. The fewer prey can support fewer predators, which then leads to abundant prey, which then leads to more predators. And this is sort of a balancing act. So negative feedbacks or dampening feedbacks, again, better term for it, what they do, because their effect is sometimes very positive, what they do is actually buffer or or actually keep from going out of equilibrium. So where an amplifying feedback will cause a disequilibrium, a buffering or dampening feedback's goal is to keep the system in check. And you can think of a lot of different examples of these, of course. I mean, adding a medication to your body when you have a bacterial infection is a kind of you're sort of adding a negative or dampening feedback, trying to keep your body from your system in a sense of equilibrium as you fight off that disease. So anyway, foxes and rabbits, classic example. So you can see what happens here is as the prey population goes up, so does the fox population, and then eventually that drives the prey population down, and so forth. There's a direct relationship between the two. So revisiting the rainforest example here, if we cut down a whole lot more than just one tree, say in the tropical rainforest, and this has been big in the news lately, of course, in the Amazon specifically, you end up with fewer trees, less water being pumped into the atmosphere through transpiration. Rainfall decreases over the area. It does affect the weather significantly. Temperatures are rising anyway, which is going to now lead to more drought, wildfire increases, and so forth. And we've been seeing that in the Amazon year after year now as more deforestation occurs. More trees die and decompose, get burned, releasing more CO2, which then leads to more temperature rise. This is an amplifying feedback. How do you combat an amplifying feedback? You combat it with a buffering or reducing feedback. In this case, if you were to reforest the Amazon, for instance, very simplistic way of doing it, if you just reforested those areas where you cut trees down, eventually you would have the net effect of balancing this whole system out. As it stands right now, that's not what's going on. All right, well, that's our last slide for this. I hope this was a good explanation of systems and how they interact and how the Earth system itself interacts. And feedbacks occur. We'll be talking more about this as you get into the activities for this module. So thank you for your time. Hope you enjoyed.